Okay, now we're going to take those forces and use them to help us draw what's called free body diagrams, and sometimes they're also called force diagrams. All right? Okay, for free body diagrams, you draw arrows to represent whatever forces you have acting on an object. So let's go through an example. If I have a book held at your hand, so we have book in hand, and I say draw the free body diagram of a book in your hand. And you want just the free body diagram of the forces on whatever object you're talking about. So here's my book. I have the weight of the book is going down. My hand upward on the book is the normal force up. And that's it. Now, if these forces are equal and opposite, then there can be no motion. The book's just sitting there in my hand. Now let's look at some pictures of free body diagrams and how we make them. And this one is just showing you applying a force from the hammer to the nail. So you would have an applied force going in the downward direction, and you always have your weight going in the downward direction. So our net force would really be these two combined because they're both going in the downward direction. Let's look here to the left. I don't really like this way, this arrow that was drawn here. Let's say that our race car is going to the right. It's traveling to the right. Okay, so the engines have put an applied force, the thrust, due to thrust of the engines to the right. We have our weight that's going down, so I'm going to label that F sub G. Our normal force was F sub N. And we do have the force of friction here, F sub F. So those are the forces that are on. Now, the acceleration, and we'll get into this when we get into Newton's second law, but the acceleration of this car is based on whatever applied force I have above and beyond the force of friction. Because to just get the car to barely move, you have to equal the force of friction. And then anything else you put on top of that then can cause the car to accelerate. So we will look into that. Well, let's look at here. Here is a guy pulling a crate. So if I draw this, he's pulling in this direction. So that is my applied force, a special case though when it's a rope, so we'll call that tension. What else do we have? Well, we always have our, and you must apologize, I must apologize for not drawing very straight lines, but I think you get the gist. My vertical vector down is your weight. I do have a surface that it's on, and that is the normal force. And it's F sub N, sorry. And then I do have friction that also is opposing this in that direction, okay? And those are all the forces that are on that crate. Let's look at this example, okay? So we have an applied force, F sub A, I'm gonna add the A in there, because my hand is pushing on that physics book. We do have my, and you can see that everyone uses slightly different connotations, but F sub G, that is my weight. And then we do have the F sub N. Now, I like to draw it rather than in this direction, though it's not wrong to draw it in that way. I like to draw that then up here, up here vertical, F sub N, okay, which is my normal force, okay? Now, what we want to find, if we find the net force in this case, you just add up all the forces. So a net force in this case would be my Fn is positive because it's going up, plus, or we could just say minus, but plus a negative Fa, and then minus Fg, or plus a negative Fg. So my net force that I would have in the downward direction, you would have your Fa and your Fg, and then you subtract from it that normal force that is keeping that up, okay, to find the actual net force going on vertically. Okay, let's look at some other examples. Let's say we have a filing cabinet that we're pushing across the floor. So let me draw my filing cabinet, and we'll say we're pushing it across the floor to the right, and it's accelerating to the right. Draw the force diagrams. Okay, all the forces. So we have our filing cabinet. We're accelerating it to the right. I have my applied force. And I'm even going to be a little more conscious of drawing these more proportional. I have force of friction opposing that, but it is less than the applied force because it's accelerating. My net force has to be in the direction to the right. I always have my weight, and I have my normal force counteracting the weight, keeping that up. So those are all the forces in my filing cabinet. Now, let's say that we have a ball hanging from a string. There's my ball hanging from a string. What are the forces? Well, I'm always going to put in my FG. Ball hanging from the string, so that means there's an applied force or a force due to tension holding that ball up. And if it's sitting there, it's in equilibrium. My net force is 0. Okay? And all is good. Now, what happens if I take some scissors and cut this string? Just cut it right off. What are the forces now on that ball as it falls? I simply have gravity. The ball's falling due to gravity. I don't have any upward force. Now, you could make the argument maybe for air resistance. But oftentimes, if the air resistance is negligible, we will tell you to discount it. And in this case of a ball falling, the air resistance would be fairly negligible. Okay? So I hope you have a better understanding from this short little video on how to draw free body diagrams. And then we'll look at why they're so important as we get into Newton's laws, and especially his second law, and how to put some numbers in all of this and make it a lot easier if you know how to draw the diagram. Now let's look at the pictures. Let's look at some other examples. So we have a filing force. This one is just showing you applying diagrams. Draw my filing pushing on that. So you would have, and do have my, and it's accelerating that everyone always have your weight orientations. Okay, draw arrows to represent my cabinet, whatever force, and then you have accelerating it to the right. I like to draw it rather than, and I know it's not wrong to draw it really like this. I like to draw that portion. I say, I have to say that but it is less than normal. And you want because right, it's accelerating what net force everyone's have put in this case. I always have my weight add up. I have all the forces. I have my net force. Reacting the way would be my Fn is on the positive because it's going up, are all the forces of N. And we do have force negative. Let's say that we have a ball, then we can have motion. The book's just sitting there. So those are the forces that are on. So my net force, the acceleration that I would have in the downward direction, acceleration of the string. So that means there's an applied force or based on whatever applied force I have above and beyond my net force is 0, because just get the car to barely move. All is good. Now, what happens if I take some scissors we have and then anything else right on top of that? I have what are the forces just sitting in here? We will look into that. I simply have. Let's look at here. How would we draw the force? Here's a guy pulling a gravity. I don't have any other force. I draw. And there's now you could make the argument in this direction. Maybe for that is my applied force, a special case though when it's a rope air resistance is negligible. What do we have? What else do we have? So I have a way to. We always have our and is supporting it. So that's my F. And not drawing very straight. That's my force. I think you get. I hope you have a better understanding vector down is your from this short. I do have a surface. What about that is on a ball? Just after the string that was they're so important as we get into Newton's laws. And especially second law, and then I do have friction. Put some ball being suspended by and make it a lot easier if you know how to draw the so let's draw the force diagram. And those are all the. If we have a ball suspended by a string, that crate, the tension now is for a level surface, and the my Fn is equals my F. If that string breaks, and you no longer have that tension, anytime that we have all you have is Fg. So any object that is just falling is going to just have the weight vector down.